All right. Thank you very much so I'm going to talk about duct tape initial data and how to create binary initial data for boson stars. And so this is a trick that to generate binary initial data. However, we applied it for boson star. However, the general trick might be also applicable to different compact objects that you might want to study. So first of all, we are users of Geochamber. So we are a numerical GR code with adaptive mesh refinement, and we have fully open source. I think it's a very flexible code. So this one is very good if you do things that go beyond binary black holes. So for example, some of our collaborators who very kindly provided me these videos, they worked on high dimensional black hole. We worked on cosmic strings too. On inflation. We also do black holes, of course. And also recently we worked on dynamic friction in a scalar field background. So again, quite it's for more problems that are on the exotic side of numerical relativity. First, furthermore, this is the major selling point. Is of course it's the adaptive mesh, and you hear this is a bit of a show-off example where you can see our infalling cosmic string loop and how the adaptive mesh is very neatly following the regions of interest. Now, lastly, we are a small team, and I feel very happy to be part of. I mean, thanks to them, I'm of course the scientist I am today, so I feel very honored to be part of this excellent collaboration. So just gonna small introduction about boson star. Of course, boson star, unlike normal stars, are made of bosons, and that's the main difference. Of course, normal stars are made of fermions, and neutron stars are made of fermionic particles. And so boson stars you can describe using a scalar field phi. And here you, of course, have the axis x and y in this representation here. So this follows more more as a wave equation. So if you set up such a Gaussian, it's very similar to throw like a pebble in a pond. You would just expect that dissipates towards infinity like a spherical wave. However, we are coupled to gravity. So the own self-gravity of this Gaussian will contain this wave from propagating out. And so what you have, if you balance these forces very well, is you have effectively a wave in a gravitational well. It's very similar to the quantum mechanical wave in a box problem I think lots of us have seen. And of course, you can then now find many solutions, and you can write a mass versus radius diagram very similar to neutron stars, and you have a stable and unstable branch. And also very similar to neutron star, you can use a solver to find these ones. So similar to solving the TOV equation, you can write a solver to find for these ones. I wrote one myself. It typically doesn't take you very much. I made this just for future people to avoid the work to do this. So if you are in need, feel free to download this one. Lastly, of course, you have to transfer this into initial data. And so we just decompose this one in gamma ij and kij. And of course, now additionally, we have also here phi and pi because we are dealing with scalar fields. This contains the scalar field information. So how does this look like? In the upper panel, you can see the energy density rho as through a slice to the boson star. And we're also trying to track the size of this one. So these are Gaussian, so they're technically infinitely extended. They're not directly Gaussian, but they're very close to Gaussian. And so what you have to choose what we choose is we take the maximum energy density and then see when the energy density goes below 5%, and that's what we choose as a size. And we try to track this. This is a single star, and when I play the simulation, what you see is going to happen is just oscillating. It sits there and oscillates. It's just what these specific boson stars do. There's other ones who don't do this, but we just happen to have to choose these ones. Now, what you can do now, if you want to have binary data, but you have this already single star data, which is fairly easy to get, is you can superpose them. And here the idea is, say you put them infinitely far apart, right? So you put the second one here infinitely far apart, this becomes effectively delta ij. And so both of these terms cancel away, and what you get is only one in a star, your single star, and that is a good, and this of course fulfills constraint. In general, of course, in GI you cannot superpose initial data, so in general this would be not possible. But of course, since asymptotically flat, this in theory works. And of course, we can do this also for all other quantities, just straight superpose them. And yeah, so now we're gonna try to see what happens. So now we're gonna set the binary up and see how they collide. However, we're gonna put an action camera around it, and we're gonna follow the star as it falls in. So now this is what we're going to see in the next panel. You can see the upper panel again as before, the energy density, but now it's an action camera. It follows the star as it falls in. And again, we try to measure the 5% size to give us over time. And now you can see, of course, it has this high frequency oscillation, but it also goes down and then comes up again, and then goes down and merges very shortly afterwards here. Now the question is, well, is this physical? And that was our question initially, and the answer is we found it's not. This is almost extremely similar to squeezing a star, right? So say you squeeze a star, and that's what we have done as an experiment to confirm this. So we've taken a single star, we squeeze it a bit and see what happened. And this is again what happens. So this again single star, not anymore binary, and see what happens. We just squeeze it by 0.1%, it's very, very little. And you can see it has the same breeding behavior as we just saw before. So it seems now that we kind of accidentally squeezed the star, but we never explicitly squeezed the star. And the reason why we squeezed this, we accidentally did this by changing the metric in the center of the star. So how can we fix this? So we can fix this now by changing this one from the delta ij to hij, right? So now how do we exactly choose hij here? We choose it to be the other metric. Again, this only works for equal mass, so it doesn't matter if you choose 1 or 2 here. Evaluated at the center of the first one. Right, so x1 is the center of the first star here. And now I evaluated this whole expression at the center of the first star, and you're gonna see these ones cancel away, and you get back the metric in the center of the first star. Again, this is an equal mass. This only works for equal mass, so it doesn't matter if you do this for second or the first star. This index can be exchanged. But the idea here is to reconstruct the metric in the center and make sure that this works well. And if we do this, this is our result. And what you can see, it's almost perfect. There's none of this excitation, none of this long wavelength excitation we see anymore. At the end, we see some deviation, but this is purely due to tidal deformation. And then, of course, they merge. So it's surprising how well this works. And it's effectively just adding a slightly different number. So it's a fairly neat trick with very, very little effort. But maybe just giving you some more intuition why this works. So if we look here at the binary system, right, and we focus in here a bit, so we just focus on one star, and we look here, we slice through and we look at the volume factor. So if you want to get the physical volume, you integrate with the square root of the determinant of gamma. That gives you how much coordinate volume corresponds to physical volume, and you would integrate to get the volume. Now this gives you a way. This gives you a way of how squeezed to determine how squeezed your star is. So this one is the naive superposition. This one is the single star. The black one is the single star. And the green one is the fixed superposition. And you can see in the center of the star, fixed and single almost perfectly match. However, there's a 2% difference between the naive superposition and the fixed one and the single star as well. So this 2% difference causes this squeezing of the star and thus all of the problems that we have. And by choosing this slightly different metric, you get some very fortunate side effects. For example, the Hamiltonian constraint, the initial Hamiltonian constraint through the center of the star, right, just reduces by an order of magnitude. And so just by applying this trick, you have an order of magnitude reduction of energy density. Furthermore, it helps you with having better radiated energy with initial radius. So if you have two stars and you collide them, and so if you put them too close, they might not have time to accelerate to the right velocity. And so you have to put them further apart to mimic effectively that they're coming from infinity. We cannot do infinity, of course, but we can do some finite distance in numerical relativity. And with this fix, you can put them much significantly closer, thus making your simulation significantly cheaper. But thanks to Ulis, who has performed these simulations. This is not exactly an oscillaton; it's a mini boson, boosted mini boson star. So this is not exactly the oscillaton I was talking before, but it also applies for oscillotons. So this is just the data I had available for the moment. Just giving you a bit of a conclusion and some caveats, right? This is a fix, right? It's not a complete solution. This is like duct tape, right? You have like a leak and you can duct tape your pipe, and maybe this maybe will hold for a long time, but at the end you still want to have a more proper solution. You want to exchange your pipe with one that doesn't have a leak anymore. So, but of course that is much more work, and this at least duct tape will solve 90% of the problems, and is a surprisingly considering the cost, extremely effective method. One other thing to point out, at least this naive specific methods, a way to fix this, only works for equal mass, and the asymptotics are slightly changed. So these are some of the caveats. But yeah, well, thank you very much for listening, and I hope this will help you out and improve your simulation. Thank you very much.